All right. Hi, everyone. I'm Miss Turk. I'll be your AP Chemistry teacher. So we're going to get started with our summer work notes with this video. And just remember, if it feels like this video is going too fast, if it feels like you need more time, feel free to rewind the video, rewatch the video. It's designed to be rewatched. Okay, so it might feel a little bit fast, but feel free to rewatch it, rewind it, slow it down. Feel free to email me if you need clarification or some one-on-one help from me this summer. I'm happy to help. So just remember, you were recommended for AP Chemistry by a science teacher at FLC because they believe that you're up to the challenge. So I believe that all of you, I've seen your academic records, are up to the challenge of AP Chemistry. But that doesn't mean suffer in silence. Feel free to please reach out to me, though, if you want some extra one-on-one help over the summer. All right, so to start with Unit 1, Lesson 1.1, which is the first lesson in Unit 1, be sure you rip off the periodic table that's on the front of your summer packet. We'll be using that. And be sure you have a calculator, like a scientific calculator. These are the types that we're going to be using in class. So I'm going to be using this. But if you don't have this, that's fine. You could use, your phone calculator. Just be sure on the phone that you press this button up here and choose scientific, because we're going to be doing a lot of exponents and stuff like that. So whenever you need to type in an exponent, like let's say you needed to do 10 to the 23rd, you would do 10 and then press this x to the y and you would do 2, 3. Okay? And then you would continue on with whatever. Okay? All right, so with that, let's get started. So 1.1 is about moles and molar mass. Okay? So as you learned in chemistry, a mole is a number of things. Okay? Just like if you have a dozen donuts, that's 12 donuts. Or if you have a pair of shoes, that's 2 shoes. If you have a mole of atoms, that's 6.022 times 10 to the 23rd atoms. So this is obviously a very big number, okay? The reason it's so big is because atoms and molecules are so small. So they wanted to group them just like bakers and people who sell flowers group things into dozens because that's a good amount to sell. A mole is a good amount of atoms or molecules because it's big enough that we can see it, okay? If we have a mole of carbon atoms or a mole of water molecules, that's enough that we can actually see it in the lab. Whereas like a dozen atoms, we can't see that, okay? So it's a big number on purpose. So let's say we wanted to convert, there's some typos in here, so change this from particles to moles, okay? So write down this example question. You can pause the video and copy down this question. So if we wanted to know how many moles are in 8.0 times 10 to the 24th molecules of water, we would do what we call dimensional analysis. If you did not learn dimensional analysis in chemistry, you can pause this video and just watch find a YouTube video about dimensional analysis, and it might refer. You might have learned it and you just don't know it's called dimensional analysis. But we're going to be using dimensional analysis to convert 8.0 times 10 to the 24th molecules into moles, okay? So we're going to do that by putting the number they give us over 1, okay? So 8.0 times 10 to the 24th molecules over 1, okay? We're going to put a time sign, and the whole point of dimensional analysis is to convert units, to get rid of molecules and get into moles. So to get rid of molecules, we're going to be sure that that's the unit of the denominator in this next factor, okay? So leave some space for a number. We don't know what number is going here yet, but we're going to write molecules on the bottom. Leave some space for a number, okay? And we want to know how many moles. That's the unit we're trying to get to. So that's going to be in the numerator. Moles is abbreviated MOL. Okay, molecules doesn't have an abbreviation, but moles is abbreviated MOL. Okay, and this factor is called a conversion factor. Okay, we're using this to convert from molecules to get rid of molecules and get to moles. Conversion factors need to be equal to 1, which means the top and bottom need to be equivalent, okay? So we know a fraction like 4 over 4 is equal to 1 because the top and bottom are equivalent. But another way to another type of fraction that can equal 1 is something like 60 seconds for every 1 minute. Okay? I know you're like, well, that's 60 over 1. That doesn't equal 1. But they have different units. 60 seconds and 1 minute are the same amount of time. Okay? Different numbers, different units, but the same amount of time. This is also a fraction that's equal to 1. And this is the type of fraction we're going to be using as our conversion factor, where the units are different, the numbers are different, but overall it is equal to 1 because the top and bottom are equivalent. So if you look up here, a mole, 1 mole is 6.02 times 10 to the 23rd particles. A particle of a substance, depending on what it is either atoms. So if it's an element, it contains atoms. If it's a compound, it contains molecules. So a mole of carbon contains 6.022 times 10 to the 23rd atoms. A mole of carbon dioxide contains 6.02 times 10 to the 23rd molecules because it's a compound. A molecule is a group of atoms bonded together. Okay? So clearly here, because we're talking about H2O, water, water is made of molecules, each molecule containing 2 H's and an O. So that's why we're using molecules rather than atoms as our particle here. Okay, so a mole represents 6.02 times 10 to the 23rd particles. So in this instance, a mole is 6.022 times 10 to the 23rd molecules. That means 1 mole is equal to 6.022 times 10 to the 23rd molecules. These are equivalent. A mole is this many molecules. Okay. So we're going to cancel molecules, okay? And then we're going to multiply straight across the top in our mind. 8.0 times 10 to the 24th times 1 is 8.0 times 10 to the 24th. Then we're going to multiply straight across the bottom. 1 times 6.022 times 10 to the 23rd is 6.02 times 10 to the 23rd. And then we're going to simplify that by doing the top divided by the bottom. So you'll type into your calculator 8.0 times 10 to the 24th divided by, okay, and everything that's in the denominator, be sure you put it in parentheses. Open parentheses, 6.022 times 10 to the, this little, on a scientific calculator, that gives you your exponent, 10 to the 23rd, close your parentheses, okay? And we're going to round that off to 13 point, or we can just round that off to 13, okay? So that's equal to 13 moles, okay? So molecules canceled out and our units are in moles. So that's what dimensional analysis does. It's a way of multiplying by a conversion factor, taking a number or a measurement, multiplying by a conversion factor, and changing the unit, okay? And just double check to be sure your answer makes sense. We have 8.0 times 10 to the 24th molecules. We know that's going to be more than a mole, okay? Because we know 6.022 times 10 to the 23rd particles is 1 mole. And this is a bigger number. So we know our answer is going to be more than a mole. So 13 moles makes sense, okay? Now let's go the other way. Now I'm going to give you the moles, and I'm going to ask for the particles, okay? In the first example, I was asking for we were dealing with molecules. In this second example, we're going to be dealing with atoms, because carbon is an element, so it's made of atoms of carbon, whereas water was made of molecules. So how many atoms are in 0.76 moles of carbon? So once again, we're going to start by putting what they give us over 1. 0.76 moles, MOL, over 1. Set up your conversion factor. Okay, don't put any numbers in here. Okay, just put moles on the bottom because we know that needs to cancel out. Okay, and on the top this time, we're going to put the unit we're trying to get to. We're trying to get to atoms. So atoms is going to go on the top. Okay. And now we got to make this conversion factor equal to 1. We've got to make the top and bottom equivalent. Okay. So we know there's 6.022 times 10 to the 23rd atoms in a mole. Okay, so the 6.022 times 10 to the 23rd goes where atoms is, okay, which here is on the top. 6.022 times 10 to the 23rd atoms for every 1 mole, okay? So the top and bottom are equivalent. This time, here the 1 mole was on the top, here the 1 mole is on the bottom, okay? Because we need moles to cancel out this time, okay? So then you just multiply straight across the top, 0.76 times 6.022 times 10 to the 23rd, okay? And we're going to just round that to 4.6. The E means times 10 to the, okay? So don't just ignore that, okay? That's an important part of the number. So we're going to round this to 4.6 times 10 to the 23rd. 4.6 times 10 to the 23rd. And the units that didn't cancel out, the units we're trying to get to, is atoms. Okay, 4.6 times 10 to the 23rd atoms. And just stop and be sure that answer makes sense. We're dealing with less than a mole of carbon. Okay, 0.76 is less than 1 mole. If there's 6.022 times 10 to the 23rd atoms in a mole, and we have less than a mole, it makes sense that our answer would be a little less than 6.022. Okay, 4.6 times 10 to the 23rd. So that's what we would expect because we have less than a mole. Okay, so that's how you convert from moles to molecules or atoms, or you convert from molecules or atoms to moles. You use Avogadro's number. That's what this is called, Avogadro's number. And this number is on your formula sheet, okay? Right here. So you don't have to memorize it. You'll have this formula sheet on the AP exam, okay? And just keep in mind that this can be, Avogadro's number is the number of particles in a mole. So you can either make the conversion factor 6.022 times 10 to the 23rd particles for every 1 mole, or you can think of it as 1 mole for every 6.022 times 10 to the 23rd particles. These are both equal to 1, okay? For the first example, we've had the particles on the bottom and the 1 mole on the top, like this. For the second example, we use this style, where we had the particles on top and the 1 mole on the bottom, okay? I remember when I learned dimensional analysis, I was very confused by the fact that you could just flip this fraction, because normally fractions are not flippable, okay? I was used to 3/4, okay? If you have a fraction like 3/4, you cannot flip that. 3/4 is not the same as 4/3. You can't just flip it whenever you feel like it, okay? But when the fraction is equal to 1, you can, okay? A fraction like 4/4, you can flip it and you get 4/4, okay? Or a fraction like, I don't know, 60 seconds for every 1 minute, you can flip that, 1 minute for every 60 seconds. Either way you flip it, it's equal to 1, okay? So conversion factors, because they're equal to 1, they are flippable. So you can flip this relationship depending on what unit you need to cancel out and what unit you need to keep, okay? All right, so Avogadro's number, 6.022 times 10 to the 23rd, that's the number of particles in a mole. Molar mass is the number of grams in a mole, okay? Molar mass varies depending on the substance. So if you have a mole of carbon atoms, that's going to have a different mass than, say, a mole of sodium atoms, right? Carbon atoms are lighter weight than sodium atoms. Okay, this is carbon, this is sodium. So if you have 6.022 times 10 to the 23rd atoms of carbon, that's going to be lighter weight than 6.022 times 10 to the 23rd atoms of sodium, which is going to be heavier. A mole of carbon and a mole of sodium have the same number of particles, but the mass of a mole is going to be different because the particles have different masses, okay? So molar mass is something that varies. It's not going to be a number on your formula sheet, okay? So molar mass is the mass of 1 mole of the substance, okay? So if we wanted to find the molar mass of water, okay, what we would do is look on our periodic table, okay? These masses on the periodic table that we think of as atomic mass are also the molar mass, okay? So for beryllium, there's 1 atom has an average mass of 9.01 AMU, okay? So you can think of this as the number of AMU per atom. So you don't have to write this down. The stuff I'm writing on a Post-it, you don't need to write it down, just listen, okay? So beryllium, it's 9.01 AMU. AMU is atomic mass unit per one atom. Okay, an AMU is a really, really, really small amount of mass. Okay, so the atomic mass tells you the number of AMU in an atom. Unfortunately, this is not useful in the lab. Okay, our scales in the lab do not measure in AMU, they measure in grams because an AMU is way too small. Individual atoms don't work for us in the lab. Okay, individual atoms, we cannot see individual atoms. Okay, so counting out atoms and measuring an AMU is just not practical because atoms are so small. So what Avogadro did was he scaled up AMU to grams. Okay, so he scaled up AMU to grams. Somehow, I'm not sure how he figured this out, he realized that there were 6.022 times 10 to the 23rd AMU in a gram. So he scaled AMU up to grams, and then he scaled atoms up to a mole of atoms. Okay. So he took 9.01 AMU, multiplied it by 6.022 times 10 to the 23rd, and he got grams. He took atoms, multiplied it by 6.02 times 10 to the 23rd, and got a mole of atoms. Okay, so essentially by scaling up the numerator and denominator by the same amount, he ended up with the same mass, but instead of AMU per atom, it can also be thought of as grams per mole of atoms. Okay, so this is what we call the atomic mass. This is what we call the molar mass. Okay, so if that whole little aside didn't make a lot of sense, don't worry about it. Okay, I'm just giving you some background knowledge, but in any case, what I want you to remember is that this number on the periodic table can be thought of as the atomic mass, the AMU in one atom, or it can be thought of as the molar mass, the grams in a mole of atoms. This is more useful in the lab because our scale measures in grams. A mole of atoms is enough that we can see it and do experiments with it. So we tend to, for lab purposes, talk about these numbers as the molar mass. Okay, so the molar mass of sodium is 22.99. That's the mass of a mole of sodium atoms. Whereas carbon is only 12.01 grams for a mole of carbon atoms. Okay, so think of this as the AMU in one atom. Also think of it as the grams for a mole of atoms, okay? And as the atoms get heavier and heavier, the grams in a mole of atoms also gets heavier and heavier, okay? So the molar mass is something that we find on the periodic table. So if we wanted to find the molar mass of magnesium, it's 24.30 grams per mole. If we wanted to find the molar mass of carbon, it's 12.01 grams per mole. It's right there, okay? If we wanted to find the molar mass of a compound, we need to add up all the individual masses of the atoms. Okay, so if we wanted to find the molar mass of water, we would do the molar mass, MM is molar mass of hydrogen, and the molar mass of oxygen. So the molar mass of hydrogen is 1.008. The molar mass of oxygen is 16.00 grams per mole. And notice in water, there's two H's and one O. The O doesn't have a subscript after it, so we know in our mind that it's a 1. So we're going to multiply hydrogen's molar mass by 2, whereas oxygen's molar mass will just be multiplied by 1, okay? And then we're going to add those together. So you have 2.016, and then this is still 16.00. And you're just going to add them together and just round off to the nearest hundredth. Round off to 2 digits after the decimal, okay? So you get, I'm just going to round that to 18.02, okay? So that's the molar mass of water. That's the grams in a mole of water, okay? So molar mass is something that we have to get from the periodic table. And you can turn this into a conversion factor as well, okay? Just like Avogadro's number was the particles per mole, this is the grams per mole. So you can write, if you were to write grams per mole as a conversion factor, it would be 18.02 grams for every 1 mole. So 18.02 grams per 1 mole. Or you can flip it. You can think of it as 1 mole per 18.02 grams. 1 mole for every 18.02 grams. So again, the top and bottom are equivalent. This is a flippable relationship. You can flip it whichever way you need to when you're doing your calculations, okay? So now we're going to bring all that together. So here we converted from moles to particles, particles to moles. Here we learn the relationship between moles and grams. So we're going to use this to convert between moles and grams. Okay. So when we bring all that together, the converting between particles and moles like we did up here, okay, this is when we're going to use Avogadro's number, okay. Avogadro's number, again, is on your formula sheet, 6.022 times 10 to the 23rd. And then to convert between moles and mass, we're going to use the molar mass. That's what this is, okay? And the molar mass is on your periodic table. You're going to use your periodic table. Molar mass varies depending on the substance you're talking about, whereas Avogadro's number is always the same for every substance. Just like a dozen is always the same. There's 12 things in a dozen. It doesn't matter if you're counting roses or bagels or atoms. So Avogadro's number is always this number of things in a mole. But the mass of a mole varies. Okay, so that's when you use the periodic table. So if we were to bring all this together, okay, we would use this kind of chart to help us answer a question like this. If the odor of C6H10S can be detected from 2 times 10 to the negative 13th grams in 1 liter of air, how many molecules of C6H10S are present? So this is our mass, and the question's asking how many molecules are in there, okay? This is a pretty small mass, okay? But even though it's a small amount of mass, it's probably still going to have a lot of molecules, okay? Because molecules are really, 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 really small. So what we need to do is convert from grams to molecules, okay? So what we're going to do is use our chart. We can't go directly from grams to molecules. Moles provides that bridge, okay? Moles provides the bridge between grams that are useful in the lab and molecules or atoms. So we can't go directly. We got to go from grams to moles first and then from moles to molecules. So to go from grams to moles, we're going to set up our dimensional analysis, okay? So we're going to put the number they give us over 1. So 2 times 10 to the negative 13th grams over 1. Put your time sign, and always throw this unit under the bus. Don't try to put any numbers first. Don't say, well, what number do I put here? Do I put Avogadro's number here? Do I put a 1 here? Don't think that way, okay? First, get your unit on the bottom and unit on the top, then we can start thinking about numbers, okay? So I'm just getting started here. We need to go from grams to moles, and then we'll deal with this. So we want to go to moles, so I'm going to put moles on the top, okay? The relationship between grams and moles is the molar mass. We're going to use the molar mass from the periodic table, okay? So this is kind of a bigger compound right here. We've got to add up, just like here we added up 2 H's and 1 O. Here we've got to add up 6 C's, 10 H's, and 1 S, okay? So the molar mass of carbon is 12.01, and we have 6 carbons. And then the molar mass of hydrogen is 1.008, and we got 10 hydrogens. And then the molar mass of sulfur is 32.06, and we only have 1 sulfur, okay? So I'm just going to type this all in my calculator in one fell swoop and add them up, okay? So do 12.01 times 6 plus this times this plus this times this, okay? And then, so I usually just add everything up in one fell swoop. 12.01 times 6 plus 1.008 times 10 plus 32.06. Okay, and we get 114.13. And again, remember, this is the molar mass. Molar mass is the grams in 1 mole of substance. It's the grams per mole, okay? So if we take this, just like up here, we converted it into some conversion factors. We can do the same thing here, okay? It's 114.13 grams per mole, okay? So the 114.13 goes where grams is, which here happens to be in the denominator for every 1 mole, okay? We can cancel grams. When a unit appears on the top and the bottom, you cancel it out, which is good because we don't want to be in grams. We want to be in molecules, okay? So we made a pit stop at moles. Now we're going to go to molecules. So you can just add on another conversion factor. This unit that we want to go away goes on the bottom, okay? And the unit we're trying to get to, which is molecules, is going to go on the top. And notice your note here, to go from here to here, between these, we're going to use Avogadro's number, okay? Remember, 6.022 times 10 to the 23rd goes where molecules is, not where moles is, okay? 6.022 times 10 to the 23rd is not the moles in one molecule, it's the molecules in one mole. So 6.022 times 10 to the 23rd molecules for every 1 mole, okay? We'll cancel moles. And then we'll just multiply all the way across the top, okay? So I'm going to zoom out here so you can see a little bit better what I'm typing in. So I'm going to do 2 times 10 to the negative 13th, and then times 6.02, 2 times 10 to the 23rd, okay? And then what I'm going to do is just divide that by, and then I'll do everything on the bottom. But be sure you put the denominator in parentheses, everything in the denominator. This is actually, you don't really need to because there's only one number in the denominator, but when there's multiple things in the denominator that are being multiplied, you got to put them in parentheses. So we get 114.13, close your parentheses, okay? And that's our answer, okay? 1055287830, okay? So put some commas in there, and the unit is molecules. Okay, that's a big number, okay? But don't think you did something wrong, okay? You might have thought, well, that's so few grams, it shouldn't have very many molecules. That looks like a small number to us, but there's still a lot of molecules in that number, okay? And if we wanted to write this in scientific notation, that might make it easier, okay? To convert a number to scientific notation, just move the decimal until you get a number between 1 and 10. So I'm going to move. Okay, don't stop here. If I stopped here and put the decimal here, it would be 10.5. That's not between 1 and 10. I'm going to stop here. 1.05 is between 1 and 10, okay? So I'm just going to leave it as, I'm just going to round it to 1 times 10 to the, and the number of times you move the decimal is the exponent on the 10. Okay, so we move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.0 times 10 to the 9th molecules. Okay, or 1 times 10 to the 9th molecules. Okay, so that's a big number. Okay, that's a big number. You can leave it in regular notation, or you can write it in scientific notation, whichever one is easier for you. Okay. All right, so let's move on to the back. Okay, so on the back of that page, we'll talk a little bit about atoms versus ions versus isotopes. Okay, so as you know, an atom, smallest amount of an element, smallest unit of an element. Isotopes are atoms of the same element that have different numbers of neutrons. So if you have two isotopes, like here we have two isotopes of carbon, they have the same number of protons, they have the same number of electrons, but they have different numbers of neutrons. And that's why their mass numbers are different, okay? So they have different masses. The reason why this one has a mass of 12 and this one has a mass of 13 is that this one has an extra neutron. Okay, they're both carbon, they both have 6 protons, but this one has an extra neutron. Okay, so they have the same number of protons, so they have the same, that's because they're the same element, but they have different numbers of neutrons. Okay, and that's what affects their masses. And then an ion is, think of it this way. Isotopes are when the number of neutrons change. Ions form when the number of electrons change, okay? Electrons are on the outside of the atom. They're outside of the nucleus, so they can be easily gained and lost, okay? So when an atom gains or loses electrons, it forms an ion. and the ion has a positive charge or a negative charge, okay? So let's take, for example, like a calcium atom. A calcium atom. It has, calcium is Ca, okay? The 20 is the atomic number. That's the number of protons, okay? So it has 20 protons. And because it's an atom, it also has 20 electrons, okay? So that means overall it has a neutral charge. All atoms are neutral. They don't have a charge because the number of positive protons and the number of negative electrons is equal, okay? Now calcium atoms may have a variety of neutron numbers, but neutrons don't have a charge. So they don't affect the overall charge of the atom, which is always neutral, okay? So some calcium atoms have 19 neutrons, some have 20, some have 21, 22. Those neutrons affect the mass, but they don't affect the charge. Atoms are neutral because the number of protons equals the number of electrons. But let's say you have a calcium ion. A calcium ion is something like this. 20 protons, okay? It's calcium, it has 20 protons, but let's say it lost 2 electrons. Calcium tends to lose its 2 electrons in the outermost energy level, its valence electrons. So the electrons is down to 18, okay? You can see this is no longer neutral, okay? So this was neutral because the positives and negative canceled out. 20 positives and 18 negatives adds up to 2 positive overall. So calcium ions, because they tend to lose electrons, or have a positive charge, okay? So loss of electrons leads to a positive charge because there's more protons than electrons. Something like chlorine. Okay, chlorine is right here. Its atomic number is 17. So a chlorine atom has 17 protons, okay? And because it's an atom, the protons is equal to the number of electrons, 17 electrons. So overall, this is neutral. But when chlorine forms an ion, it tends to gain electrons, okay? Chlorine has 7 valence electrons. It needs 8 to be stable. So it tends to gain an extra electron. So we have the chlorine ion. It still has 17 protons. Protons are in the nucleus. They cannot be gained or lost, okay, in a chemical reaction, in chemistry. The electrons on the outside of the atom can be gained and lost. So chlorine tends to gain an extra electron, so it has 18 electrons, okay? 17 positive and 18 negative adds up to 1 negative, okay? So chlorine ion, because it gained an electron, it has a negative charge. We call that an anion. So cations have a positive charge. The T in cations looks like a plus sign. That's how I remember cations are positive. Anions are negative, okay? And then just an overview of our subatomic particles, protons, neutrons, and electrons, okay? When we say the mass in U, that's AMU, okay? But we tend to abbreviate it U, okay? So AMU is the unit we use to measure the mass of protons and neutrons in atoms. So essentially a proton is 1 AMU, a neutron is 1 AMU, more or less, okay? And the electrons are about 1/2000th of an AMU, way less, okay? So the electron's mass are what we can call negligible. We don't include electrons in the mass number for atoms because the mass of an electron is so small, okay, compared to a proton or neutron. These are dominant. So essentially a proton is 1 AMU, more or less. A neutron is 1 AMU, or more or less. The electron, we don't worry about it, okay, in terms of the mass. Charge, on the other hand, electrons do have a noticeable charge, okay? The charge is equal and opposite that of a proton, but its mass is pretty negligible, okay? So the atomic number, which is on the periodic table, okay, we sometimes abbreviate that Z, okay? It's the number of protons that an atom has in the nucleus, okay? The mass number is not on the periodic table. The mass number is the number of protons plus the number of neutrons. We don't include electrons because their mass is negligible. The reason it's not on the periodic table is because the number of neutrons can change, okay? Some, like I said, some calcium atoms have 19 neutrons, some have 20, some have 21. So we can't put a mass number on the periodic table because the mass number varies depending on the neutrons, okay? You might be thinking, well, this is the mass number, this number down here. That's not the mass number, that's the average atomic mass, which is the average of all the possible mass numbers, okay? So some calciums have a mass number of 39, some are 40, some are 41, some are 42, depending on the neutrons. The average mass number is 40.08 because the vast majority of calcium atoms have a mass of 40, so 40 kind of dominates. But there's a few out there that are less than 40, some more that are more than 40, so the average mass is 40.08. But the mass number is just for one particular isotope. And then, so the way that we indicate or kind of abbreviate the type of atom or ion we're talking about is with this type of notation, okay, where we put the symbol of the element here, okay, we put its mass number, A, which is called A, up high, and we put its atomic number, which is called Z, down low, okay? So here we have, I'm going to cover this up. Here we have two different isotopes of sodium. They're both sodium. They both have an atomic number of 11. They both have 11 protons. But they have different mass numbers, okay? This one has a mass number of 23. We call it sodium 23. This one has a mass number of 24. We call it sodium 24, okay? And that's because this one has an additional neutron, okay? So the protons and the neutrons need to add up to the mass number. So the protons are the atomic number. So there's always 11 protons. That means this one has 12 neutrons because 11 protons plus 12 neutrons adds up to 23. Whereas this one has 13 neutrons because 11 protons plus 13 neutrons adds up to 24. So they'll give you the protons, they'll give you the mass number, and you can from that figure out what the neutrons are, okay? Because protons and neutrons add up to the mass number, okay? Sometimes we have ions, okay? Notice this has a little charge on it. So when you see a plus sign, it means 1 positive. Or if you see a minus sign, that's 1 negative. If it's 2 positive or 3 positive, they'll put the 2 or the 3. So this sodium has a charge of 1 positive, okay? It still has the same number of protons, same mass number, but it lost an electron. This 1 positive means it lost an electron, okay? So normally, because it has 11 protons, it also has 11 electrons normally, but this clearly lost an electron. So we can tell this one would actually only have 10 electrons, okay, because of that positive charge. It's still sodium, but it still has the sodium nucleus with 11 protons, but it's no longer an atom, it's an ion, because it lost an electron and now it has a charge, okay? So it's down to 10 electrons. So what I'm going to have you do, what we're going to do here is complete this chart based on what we just learned, okay? So you're going to fill in the isotope name, the symbol, Z is the atomic number. Remember, that's on the periodic table. A is the mass number. The mass number is the protons plus the neutrons. Then the number of neutrons, the number of electrons. Remember, electrons are negative. And make a final column for the number of protons. Remember, protons are positive, okay? So the first one's been done for you, okay? It's boron. You're going to need your periodic table for this. Boron is B, okay? You can see its atomic number is 5, okay? They told you that this is boron 10, okay? Not all borons have a mass number of 10, but this one does. So if the mass number is 10, that means that the atomic number, the number of protons, and the atomic number are the same thing. So you can go ahead and write a 5 over here. The number of protons is 5, okay? And the number of neutrons is 5, so that adds up to the mass number of 10, okay? The reason why the electrons are 4 is because this has a positive 1 charge, okay? So normally it would have 5 protons and 5 electrons if it was an atom, but it has a positive 1 charge. So that means it lost an electron. So 5 positive and 4 negative adds up to 1 positive, okay? So let's try this next one together, okay? We have, each of these rows gives you just enough information to fill in everything else. So this one, it's Ca, okay? The AP chemistry periodic table does not have the names. So if you're forgetting some of the names of these, you can look it up on a periodic table online or something like that. So Ca is calcium. And And remember, this number we write after it is the mass number, that top number there. So this is calcium 40, okay? Z is the atomic number. That's on the periodic table, okay? So the atomic number for calcium, that's the top number. It's 20. And if the atomic number is 20, that means the protons are 20. Okay, those are always the same, the atomic number and the protons. The mass number is not on the periodic table, okay? Don't say, oh, 40.08. No, 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 no. That's the average of all the mass numbers. I want to know the mass number for this particular isotope of calcium, which is that top number right there. It's 40, okay? The neutrons take some work, okay? The neutrons varies. You've got to figure it out, okay? So if the protons and neutrons adds up to 40, and we have 20 protons, that means we must have 20 neutrons, because 20 plus 20 equals 40. And the electrons are 18, okay? Why are there 18 electrons instead of 20? Well, it's because this is an ion with a 2 plus charge, okay? 18 negative electrons and 20 positive protons means the overall charge is 2 positive, okay? All right, next one, oxygen 16, okay? So we'll put the 16 up high. Oxygen symbol is O, okay? And then the atomic number for oxygen, you got to look on the periodic table, that's 8. Okay, if the atomic number is 8, that means the protons are also 8, okay? If it's 8 positive protons and 8 negative electrons, that means it's neutral, there's no charge, okay? So don't put a charge on this. The mass number is the protons and neutrons added together. So the protons are 8. Sorry. The mass number was given to us. It's this number right here. It's 16. Okay, they gave us the mass number. Now we use that to figure out the neutrons. So the neutrons and the protons need to add up to 16. So 8 plus 8 equals 16. Okay. Often the neutrons are the same as the protons, or maybe a little bit more. Occasionally a little less. So, you know, you can tell you're in the right ballpark when the number of neutrons is kind of near the number of protons. All right, next one, U, okay? U is way down here. This is an element we don't use very much, okay? U is uranium, okay? So this is uranium. The mass number is not clear to us yet, okay? The mass number is not on the periodic table, but I don't know it yet, okay? But we'll figure it out. The atomic number for uranium is on the periodic table, though. That's a 92. So the atomic number is easier to figure out, okay? If the atomic number is 92, that means the protons is 92. And if we want to figure out the mass number, we do the protons plus the neutrons. So do 146 plus 92, and you get 238. So it's uranium 238, and put the 238 up high, 230 up high, and then the U. The protons and electrons are equal, so there's no charge on this uranium. It's a neutral atom, okay? Next one, okay. Actually pause the video and do these last 3 on your own. Use your periodic table, and then unpause the video and I'll go over it. Okay, so this one, the atomic number 9, right here, we're dealing with F, which is fluorine. Which is an F, okay? The mass number they gave you, it's 19. So fluorine 19, put the 19 up high. The number of neutrons we got to figure out, okay? The atomic number is 9, so the protons is 9, okay? We got to figure out the neutrons. So we know the protons and neutrons need to add up to 19. So 9 plus 10 equals 19, all right? This next one has atomic number of 17, so that's chlorine, Cl. Okay. The mass number is the protons and the neutrons together. So if the atomic number is 17, the protons is 17, okay? To figure out the mass number, we would add the protons and neutrons. 17 plus 18 adds up to 35. Okay, so this is chlorine 35, and put the 35 up high. Okay, now let's see if it has a charge, okay? It has 17 positive protons, but 18 negative electrons. So it gained an extra electron. So its charge is 1 negative, because 17 positive and 18 negative add up to 1 negative. So put a little 1 negative up there. Okay. Then this last one, okay, this one takes a little bit of work, okay? We can't tell what element it is. We don't know the atomic number. We don't know the protons. We can't figure that out immediately, okay? But we do know the mass number and we know the neutrons. So if the mass number is 32 and the neutrons are 16, what plus 16 equals 32? 16 plus 16 equals 32. So 16 must be the protons. So if it has 16 protons, the atomic number is 16. Atomic number 16, that's sulfur, which is an S, okay? And remember, we put the mass number after it. Sulfur 32, 32S. Let's see if it has a charge, okay? The electrons are 18, and the protons are 16, okay? So the atom would have had 16 and 16. This is clearly an ion. It gained 2 extra electrons. So 18 negative and 16 positive adds up to 2 negative. So that's an ion, okay? So just next to each one with a charge, let's just indicate that that's an ion. The first one's an ion, the second one's an ion, these are neutral, and the last 2 are ions. Okay, these are ions. If it has a charge, it's an ion. If it's neutral, equal numbers of protons and electrons, then it's an atom. So this one's an atom, atom, and atom. Okay? All right. Now for the last 2 exercises, just pause the video and copy those down. Okay? And these are just a review of converting between particles and moles and grams, okay? So this first example, how many molecules are in 5 grams of H2O? So like we said, we always start out by putting what they give us over 1. Here's the mistake a lot of people make, okay? They just put 5.0 over 1, and then they're like, what do I do next? You can't just put 5.0. It has to have a unit. Without a unit, I don't know what to do next. If you just show me that, I can't tell you what to do next. There has to be a unit. And then the next thing is always throwing that unit under the bus. Leave some space for a number, put that unit there, okay? The next mistake people often make is they call me up, Ms. Turk, what do I do now? Where do I put the 1? Where do I put Avogadro's number? I don't know. Until I see a unit on the top and the bottom, I don't know where the numbers go, okay? You have to put a unit on the top and bottom before you fill in numbers. So we're starting with grams, okay? And if we look back at our little chart, okay, we're starting with grams and we want to get to molecules, we got to make a pit stop at moles, okay? So we're going to go to moles next, okay? And remember, to go between grams and moles, you use the molar mass, which is on the periodic table, okay? So we're dealing with water here, so we have to add up 2 H's and 1 O, okay? Which we actually already did that. We already did it up here. We added up the mass of 2 H's and 1 O for a molar mass of 18.02 grams per mole, okay? Remember, 18.02 grams per mole means the 18.02 is the grams, it goes where G is, for every 1 mole. That's what 18.02 grams per mole means. It means 18.02 grams for every 1 mole, or 1 mole for every 18.02 grams. Okay, cancel grams. Now, next step is clearly, we got to get rid of moles, throw that under the bus, and we want to get to molecules. Okay, and remember, look at our little chart here. To go from moles to molecules, we got to use Avogadro's number, okay? And don't just guess where Avogadro's number go. Don't just say, well, doesn't the 6.022 times 10 to the 23rd, it always goes on the bottom, it always goes on the top. No, 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 no. You've got to think about where it should go. Avogadro's number is the number of particles in 1 mole. So Avogadro's number goes with molecules. 6.022 times 10 to the 23rd molecules for every 1 mole. That's the number of molecules in a mole. So moles can cancel and we're left with molecules, okay? So just multiply straight across the top. 5 times 6.022 times 10 to the 23rd. Okay, and then divide by, open your parentheses, everything on the bottom, which is just 18.02 times 1. So divided by 18.02. Okay, and you get, we're going to round that to 1.7, okay? Please don't say 1.7 molecules. First of all, you know that doesn't make sense, okay? The answer is not 1.7 molecules. If you have 5 grams of water, there's no way there's only 1.7 molecules of water. You can't even have a fraction. I don't know. It doesn't make any sense. So notice there's an E. E means times 10 to the 23rd molecules. Okay? And just double check that your answer makes sense. If we have 5 grams of water and it's 18 grams in a mole and we only have 5 grams, we know we have less than a mole, right? If it's 18 grams per mole and we have 5 grams, we have less than a mole, okay? We know there's this many molecules in a mole and we have less than a mole, so it makes sense our answer is less than 6.02 times 10 to the 23rd, which it is, okay? So we can tell our answer is in the right ballpark. All right, for this next one, now we're going from atoms to mass, okay? The mass is measured in grams, okay? So now we're going to go the other way. So we're going to start with 5,283 atoms. You've got to put your unit. Throw atoms under the bus. And again, we've got to lay our units out before we try to guess what numbers go where, okay? So I want you to pause the video and use this chart, okay? This time we're starting with atoms and going to grams. So go from atoms to moles and moles to grams. And then unpause the video and check your answer. Okay, so we're going from atoms to moles. Okay, remember when you go from atoms to moles, use the mole, sorry, we're going this way, sorry. When you go from atoms to moles, you use Avogadro's number. Remember, Avogadro's number is not the moles in one atom, it's the atoms in one mole. Okay, so cancel atoms, and we're in moles. Now that we're in moles, we can go to grams. And to do that, we use the molar mass, which is on the periodic table. Okay, so throw moles under the bus. The question's asking for mass, which is grams. So we want grams to be on top this time. So we use the molar mass here, which is on the periodic table. We're dealing with boron, B. Okay, so that's nice and easy. Okay, we don't need to add anything up. It's just 10.81. Stop and think. Is the molar mass the number of moles in 1 gram, or is it the number of grams in 1 mole? Molar mass is the number of grams in 1 mole. So this number goes where grams is, in 1 mole. Okay, cancel moles. So multiply straight across the top, 5,283 times 10.81, okay? And then divided by, open parentheses, 6.022 times 10 to the 23rd. Okay, so essentially what I did is multiply straight across the top and then divide it by everything that's on the bottom. I'm essentially doing top divided by bottom all in one fell swoop. And that's our answer, okay? We're going to round that off. Again, pay attention to the E. Okay, the answer is not just 9.483. Or sorry, 9. Did I get this right? 5,283 times. Oh, wait. Let me back up. I did 10.80. I knew my answer was a little bit off. I should have done 10.81. Okay, so 5,283 times 10.81 divided by open parentheses 6.022. Okay. So we get 9.483, and a lot of people are like, oh, 9.483. 9.483 does not make sense. Okay. If we have this many atoms, that's not that many atoms, okay? We're not able to see that. There's no way it weighs 9 grams, okay? It's 9.483 times 10 to the negative 20th, okay, grams, all right? It's a very small number of atoms, so it's a very small number of grams, okay? All right, so that is it for 1.1.